This tutorial video is going to discuss the concept of stoichiometry. And stoichiometry is something that we actually use in the kitchen all the time when we are working with a recipe and we might not have the right number of ingredients. You still want to make that recipe, and so you either adjust it to make a smaller amount or adjust to make a greater amount. And remember that that recipe for chemistry are chemical equations. So we're going to go through a couple of examples that give a more realistic view of what actually happens in the lab. So in the last few classes we talked about chemical equations. Here's a chemical equations that tells me that 3 moles of silver nitrate react with 1 mole of potassium phosphate, both in solution, to produce 1 mole of silver phosphate solid and 3 moles of potassium nitrate in solution. So we had explored the idea of what happens if you have 6 moles of silver nitrate. How many moles of solid do you expect to produce? Well, let's take a look at our chemical equation and try to figure out what is in fact our solid. And when I look at my state of matter, it looks like that S lets me know that the silver phosphate is my solid. So this is going to essentially become a mole-to-mole conversion. So we always start with our conversion factors. So in terms of the conversion factors that I'm going to be setting up, it is between silver nitrate and silver phosphate. So when I look at these numbers, it looks like for every 3 moles of silver nitrate, we're going to produce 1 mole of silver phosphate. And in the conversion factor, we can switch the silver phosphate and put that on top and place the silver nitrate on the bottom. All right, so that gives us the tools or the conversion factors available to us when we are working with mole-to-mole conversions. So I start off, and let me go ahead and put the right sig figs on this one. We'll make it 6.0. So we have 6.0 moles of silver nitrate. I always put a times sign, don't put an equal sign, and I need to find the conversion factor that has silver nitrate as the denominator. And so that's this one right here. All right, so I go ahead and put my 3 moles of silver nitrate on the bottom, my 1 mole of silver phosphate on top. These do cancel out. And so with that said, it tells me that I am going to produce 2 moles of silver phosphate. Now this is something we've seen before, and it does logically make sense, right? Let's make sure we have the right number of sig figs. Since I have 2 sig figs here, I want to make sure my answer has 2 sig figs, and I'll just place a decimal with a 0 on that. So it looks like we've doubled our recipe, so instead of having 3, we now have 6 moles of silver nitrate. We would expect double the amount. So instead of 1 mole of silver phosphate, we now have 2 moles of silver phosphate. Now, we've had these experiences in the lab where we know that moles just are not realistic to count in a lab. Instead, we use grams. And so now we can bring together all those tools that we've been using this whole semester to try to figure out how we can apply this chemical equation into the lab setting. Remember, in the lab setting, I only have the possibility of measuring grams, yet at the same time, the chemical equation is written in the language of moles. So I need to do some translation, or we can say conversion for that. So here's an example where I'm told that I use 30 grams of silver nitrate in this reaction, and I want to know how many grams of solid I expect to produce. These are things we can easily record in the lab, but remember that chemical equation is only in the language of moles. So what would be our first logical step? Well, wouldn't it be nice to know how many moles 30 grams is? And that's exactly what our first step is. So step 1 is doing the translation. I call it translation for lack of better words, where we're translating what we can actually measure in the lab to apply to the chemical equation. And so for this here, we simply do a gram to mole conversion like we've been doing the whole first semester. I look at the periodic table. I see that I have 1 mole of silver, 1 mole of nitrogen, 3 of oxygen. I add those all together, and when I do, I get 70 grams of AgNO3 over 1 mole of AgNO3. Okay, now how did I get this? Just as a reminder, these are conversion factors. I looked at my periodic table, and the periodic table tells me that 1 mole of AgNO3 has a mass of 170 grams. So I can either place the moles on the top or the bottom. I want to have these cancel out, and so it does. My answer for this one is that I have 0.176 moles. I want to keep it at 3 sig figs of Ag. Oh, and my apologies. Oh, yes, we're good. Of AgNO3. Now, can I from here go to the next step and figure out how many moles of solid I'm going to have? Remember, my moles of solid are the AgPO4. And the answer is yes. I know that it is a 3-to-1 ratio. Remember my conversion factors from before? My conversion factors tell me that for every 3 moles of AgNO3, I'm going to produce 1 mole of Ag3PO4. Okay, so I create a conversion factor where I now can cancel out my AgNO3. So the conversion factor is based on this. I'm going to do what I did in my first slide and set it up so that I can cancel out the AgNO3. So that means 3 moles of AgNO3 over 1 mole of Ag3PO4. Where did I get this from? This came from the equation, okay? My equation tells me that it's a 3-to-1 ratio. Where did this come from, this conversion factor? From the periodic table. Okay? Now, with that said, if I do my multiplication, I do 0.76 times 1, press the equal sign, and then divide it by 3. I get the number of 0.59 moles of Ag3PO4. Okay, so here's an example where we're not done yet, but I've been able to use my gram to mole conversion to translate my reactant, silver nitrate, into moles so that I can then find the relationship using my chemical equation, being the 1-to-3 relationship, to figure out how many moles of Ag3PO4 I have. The last step, it's asking me for how many grams I would expect. Now I have my answer in moles. Can I convert these moles into grams? And the answer is yes. I do now a mole to gram conversion. So I take the 0.59 moles of Ag3PO4 and I set up a conversion factor using the periodic table. So when I look at my periodic table and add up my silver, my phosphate, and my oxygen, I discover that I have a mass of 418.6 grams. So I set up another conversion factor. In this case, I want to put the moles on the bottom, 1 mole of Ag3PO4, and I put my grams on top. This allows me to cancel out my units, and there it is. And that's the case for this one as well. And my answer in this case, and remember for this one I want to have 3 sig figs, is, oh, and my apologies, this answer is actually 0.053. And this is 0.05, I'm sorry, 0.059, and this one is 0.059. And my answer ends up being 24.6 grams of Ag3PO4. So when I do this experiment in the lab, and you're going to be doing one that's similar to this, I should predict to get 24.6 grams of solid. Whether or not I do, I have to actually test it out myself, but in theory, that's what I should be getting. And that's easy to measure on a scale. So let's do a couple more of these and review where, in this case, I'm telling you how many moles you have in this reaction, but I want to know how many grams. Well, in this case, you already have your answer in moles. And again, let me do 2 sig figs for this one. I know I have 2 moles of AgNO3. I want to know how many grams of solid are produced. Remember that my Ag3PO4 is my solid. It is a 1-to-3 ratio. That means for every 1 mole of Ag3PO4 that I have, 3 moles of AgNO3 are going to be produced. I set up a conversion factor, like I did last time, to see how many moles of Ag3PO4 I'm going to make. It is a 3 mole AgNO3 to 1 mole Ag3PO4 ratio. This gives me a number of 0.66 moles of Ag3PO4. So I want to know, well, how many grams is that going to be in my beaker? And so I have the answer in moles. Can I get it to grams? And yes, it's a simple gram to mole conversion. So using my periodic table, remember I discovered that 1 mole of Ag3PO4 has a mass of 418.6 grams. So I'm going to set up a dimensional analysis, using conversion factors that are going to cancel that for me. These cancel out, and my answer is going to be 276 grams of Ag3PO4. Now keep in mind I need to have 2 sig figs, so I can round it to say, or 280 grams. That gives me those 2 sig figs. Either answer is right. I'm not so concerned about the sig figs. Okay, let's do the last one. The last one is the other possibility, where you are given 45 grams of silver nitrate. And in this case, I don't care so much about how many grams. I just want to know how many moles that's going to be. So same setup. I have 45 grams of silver nitrate. In order for me to apply this chemical equation, remember this chemical equation is in the language of moles, but I have grams here. So I need to first do a translation. So the first thing I need to do is look at my periodic table. In my periodic table, I know that 1 mole of silver nitrate has a mass of 170 grams. I'm going to set up dimensional analysis, so that's 170 grams of AgNO3 over 1 mole of AgNO3. And when I work through that number, that works out to be 0.265 moles of AgNO3. Then my equation, remember, tells me that for every 3 moles of AgNO3, I will produce 1 mole of Ag3PO4. So I can set that up into a dimensional analysis. So using my value of 0.265 moles AgNO3, I can then set up my proportions, where I know that for every 3 moles of AgNO3, it will produce 1 mole of Ag3PO4. I need to check whether or not those cancel out. They do, and my answer works out to be 0.88 moles Ag3PO4.